Okay, we're going to hone in on conditions that we need for certain special parallelograms, namely rectangles and rhombuses. So let's get started here. We're going to start with the basic theorem. If one angle of a parallelogram is a right angle, then it is a rectangle. So the argument here is that if I have a parallelogram and I have only one right angle, then I know that it has to be a rectangle. So why don't we try to prove that? Okay, so let's start off with a parallelogram. We'll call it A, B, C, D. And we'll make the measure of angle D 90 degrees. Okay, so just to clearly state some things here, we're given parallelogram ABCD, where the measure of angle D is 90, so it's a right angle, right? We want to prove that ABCD is a rectangle. All right, so let's start the proof. All right, so right off the bat, let's put down that parallelogram ABCD, and the measure of angle D is 90 because that is given to us, right? So that should be straightforward. Okay, well, we know some things here. We know that, segment AB is parallel to segment DC, so these are parallel. And segment AD is parallel to segment BC, so these are parallel, because that's the definition of a parallelogram. Okay, so that's not surprising, but if they're parallel, then A and D are same side interior angles, right? Which means that this and this have to add up to 180, so if this is 90, that one also has to be 90. So the measure of angle A has to be 90. There we go. Also, D and C are same side interior angles, which means that the measure of angle C also has to be 90. This is by the same side interior angle theorem, that they have to be supplementary. So if one's 90, the other one has to be 90. We also know that the measure of angle B has to be 90 because the opposite angles of a parallelogram are congruent. We proved that last time round. So it has to be 90. So I have all four angles equaling 90, which is how we define ABCD is a rectangle. Why? Because that is the definition of a rectangle. A parallelogram that has four right angles. So there we've proven that. All right, let's go into number 2. Got 4 more to prove today. Okay, so the second one here, I'm just going to build a drawing for it to explain it. The theorem says that if I have a parallelogram ABCD and the diagonals, that one's sloppy. Yep, we can leave D there. Right, the diagonals are congruent, then it's a rectangle. So we're going to say we're going to be given that we have parallelogram ABCD such that AC is congruent to BD. Then we want to prove that ABCD is a rectangle. Okay, so let's build this one out a bit. All right, so we first know that ABCD is a parallelogram that's given to us. That's going to tell me that segment AD has to be congruent to segment BC because the opposite sides of a parallelogram are congruent. So this guy and that guy have to be congruent. Awesome. Okay, I also know that AB has to be congruent to itself. So that's the reflexive property. That gives me this one congruent to itself. Okay, so what do we have here? We also know, we know something else. We know that AC has to be congruent to BD because we were given that, which means that this one is congruent to that one. So if you look, I now have this side, and that side of that triangle. And in the red here, I have this side, and this side of this triangle, which means that those two triangles are in fact congruent. So triangle DAB has to be congruent to triangle CBA by SSS. All right, so let's get some more space to work here. Okay, so we just proved those two triangles congruent. So we always do that basically so that we can talk about some parts of those triangles. So let's say that the measure of angle DAB is congruent to the measure of angle CBA. That's by CPCTC. So DAB, CBA have to be congruent. One's in each triangle. That's awesome. We also know that AD is parallel to BC because that's the definition of a parallelogram. That means that those two angles are supplementary. The measure of angle DAB plus the measure of angle CBA has to equal 180. That's same side interior angles theorem. Okay. But we know from up here that these things are equal, so I can say 2 times the measure of angle DAB is equal to 180. That's by substitution, which is going to give me that the measure of angle of DAB is 90 by division. And I've won it because once I have this angle, DAB being a right angle, I know the other three have to be right angles. So I can say that ABCD is a rectangle. And I can say this because a parallelogram has one right angle, means it is a rectangle because that's what we just proved in the last theorem. All right, so there's 2 down, 3 to go. Okay, so this is our first one about rhombuses. So let's get a rhombus up here. Let's call this A, B, C, D. And what we say here is that if I have 2 consecutive sides that are congruent, let's say AD and AB of a parallelogram, then it has to be a rhombus. So we're going to say given that ABCD is a parallelogram and AB is congruent to AD, then we want to prove prove that ABCD is a rhombus. Okay, so let's build this out a bit. Statements and reasons. All right, so if I know two consecutive sides are congruent, then we want to say that we have a rhombus. Okay, so let's start off with the fact that we have a parallelogram. That's given. Okay, then we know this. We know that AD has to be congruent to AB. Sorry, that's not what I want. I want DC. There we go. That's it. DC has to be congruent to AB. And I want AD congruent to BC because the opposite sides of a parallelogram are congruent. All right. So I now have the opposite sides congruent. Now it should be trivially obvious at this point that I in fact have a rhombus, but we have to make like a couple more statements here to get it in the proof. AB is congruent to AD, that's given. And finally, AB is congruent to BC, is congruent to DC, is congruent to AD, because this is using the transitive property with both this statement and this more than once. Which finally says that ABCD is a rhombus. And that's by the definition of a rhombus. Okay, so 3 down, 2 to go. We now have that if I have 2 consecutive sides, that's enough to show that it is a rhombus. Okay, so let's find another way to find a rhombus. If I have a parallelogram, let's call it again ABCD. Oops. D, and its diagonals are perpendicular. So I want to be given a parallelogram ABCD where AC is perpendicular to BD. I want to prove that ABCD is a rhombus. Okay. Yep. It's a rhombus. So let's try to do that. All right. So let's start off with ABCD is parallelogram. That's given. Okay. This tells me that AM, okay, so we're going to call this M, sorry. AM is congruent to MC, and BM is congruent to MD because the diagonals of a parallelogram bisect each other. All right, so what does that tell me? That tells me that this and this are congruent, and that are congruent. Okay. I know that all of these angles, the measure of angle AMB is equal to the measure of angle BMC is equal to the measure of angle CMD is equal to the measure of angle AMD, and they all equal 90 because this is the definition of perpendicular lines. So all of these have to be right angles, which in turn makes a whole bunch of congruent triangles. Triangle AMB has to be congruent to triangle BMC, has to be congruent to triangle, or sorry, that's CMB, has to go the other way. Has to be congruent to triangle AMD, or we have AMD already, AMB has to be congruent to triangle CMD, or we have CMD, CMB. There we go, CMB. Basically, these four triangles are all congruent by SAS, which means that AB has to be congruent to BC, has to be congruent to DC, has to be congruent to AD, all by CPCTC. And if I have all four sides being congruent, then we know that ABCD is a rhombus, because that's what a rhombus is. Okay, so that gets me 4 for 5. We have two ways of proving rectangles, or parallelograms as rectangles. We have two ways of proving that a parallelogram is a rhombus. We need one more way to show rhombuses. Okay, so our last one here is we're going to start off with a parallelogram that's going to end up looking like a rhombus. Again, we're going to call this A, B, C, and D. We're going to put in the diagonals again. So this is M, and we're going to say that this diagonal bisects that angle and that angle. And if that's the case, we're going to argue that we've proven that this is a rhombus. So we're going to be given that parallelogram ABCD such that segment BD bisects angle ABC and angle ADC, and we want to prove that ABCD is a rhombus. Okay, so let's see if we can actually do that. Statements and reasons. Let's start off with what we know. We know that ABCD is a parallelogram. We know that because we're given it. Okay, that tells me that angle ABC has to be congruent to angle ADC because the opposite angles of a parallelogram are congruent. Okay. BD bisects these angles. Angle ABC and angle ADC, because we're given that. That's not new information, which means that if this bisects that and it bisects this, then angle ABM has to be congruent to angle CBM, has to be congruent to CDM, has to be congruent to ADM, because this is the definition of angle bisector, right? So the definition of an angle bisector is it cuts it in equal parts. If the two angles are congruent, then all the parts have to be equal. All right, so what do I got here? I've got these angles all being congruent. I can say that BD is congruent to BD. That should be a reflexive property, right? So that's reflexive. So in turn, I get that triangle ADB, right? Because this is congruent to itself. ADB has to be congruent to triangle CDB by ASA. And then we're going to leverage that with CPCTC to get us somewhere. So let's pause this and make some space. All right, so we just proved the left and right triangles are congruent. That tells me that AB has to be congruent to BC. That's by CPCTC. Now I have two consecutive sides being congruent. So that means that ABCD is a rhombus. Why? Because two consecutive congruent sides of a parallelogram is sufficient to show that we have a rhombus. That was like a theorem 2 theorems back, so we have proven it. All right, so let's try to summarize what we've learned here. Okay, 2 ways to get a rectangle. 1, have a parallelogram, show that one right angle, that gets me to a rectangle. Another way is to have a parallelogram and show me that the 2 diagonals are congruent, and that will get me a rectangle. Ways to get a rhombus, right? 1 is to show that 2 consecutive sides are congruent. That would work. A second is to show that the 2 diagonals are perpendicular. And the third way is to show that one of the diagonals bisects a pair of opposite angles. Any one of these 3 would show me that I have a rhombus. Any of these 2 would get me a rectangle. So these are conditions that we can use to prove the special parallelograms. In order to prove a square, I have to prove that it's both a rectangle and a rhombus. All right, so that's it.